Hi class. In this video here, we're going to go through section 5.4, and this is titled Fixed Points, Hot Loops, and Rainy Days. So how the certainty of fixed points implies certain weather phenomena. Okay, so what's going on in this section? Times are changing, things are moving, the world is always in flux. With all this movement, it is comforting to find settings where stability is absolutely required. Not by statue or costume, but by the higher law of mathematics. Not by statue, excuse me. Here we'll examine various instances where things must remain fixed and consider some surprising applications and consequences regarding the climate on Earth. Okay, so we have this thing called the rubber breakup challenge, and this is an introduction to one of the most what we're driving towards at the end of the section. So consider two disks. One is red and one is blue, and they are identical in size. Okay, the only difference between the two discs, besides their color, is that the red one is made of an extremely stretchable, shrinkable, or distortable rubber. Okay, whereas the blue one is made of rigid material, so it is unbending and cannot be distorted. So you can see how this is all building towards something, right? Like we were talking about rubber geometry early on, and so now we're again here the red disc is going to relate back to that. Okay, so we are handed these discs, the red one on top of the blue one. Since they are the exact same size, each point of the red disc touches one and only one point of the blue disc. And similarly, each point of the blue disc touches one and only one point of the red disc. So we have paired the points of the red disc with points of the blue disc, okay? Each one has a partner, okay? So there's one. Think of them as paired points, okay? In other words, we found a one-to-one correspondence between all the points on the two discs, okay? So here's the challenge, okay? So of course the world is in flux. Suppose the red points start to dance around, okay? And that is, we suppose we lift up the red disc, stretch, shrink, fold, bend, twist, and otherwise distort it, but no cutting, and then place it back on top of the blue disc. All right. The only rule is that the red disc cannot hang off the blue one. That is, the red disc must sit completely on the blue, but in any way, shape, or form that you wish. Plainly, we have mixed up and destroyed some original pairs of partners of points. In fact, there may be some blue points that have no red points above, like you can see right here. Okay? There may be other blue points that have exactly one red partner, but that partner may not be its original correspondence one. Here's the challenge. Can you find a distortion of the red disc so that once it is placed on top of the blue disc, no red points is paired with the original blue partner? That is, each original pair of partners had a breakup. Try to distort the red disc in an attempt to have every point of the red disc move from its original position. And so intuitively, you might be like, oh, obviously I could do that. Not a problem. There has to be some way I could distort it so that there's none of the original pairings are the same. Well, it turns out that you can't. It's impossible to stretch, rotate, distort, fold, or squish the red disc and place it back on top of the blue disc. Okay? In such a manner that each point of the red disk moves. This surprising fact is a mathematical result known as the Brouwer fixed point theorem. And it just says this. Suppose two disks of the same size, one red, one blue, are initially placed so that the red disk is exactly on top of the blue disk. If the red disk is stretched, shrunken, rotated, folded, or distorted in any way without cutting, and then placed back on top of the blue disk in such a manner that it does not hang off the blue disk, then there has to be at least one. There could just be one, but there has to be at least one point on the red disk that is fixed. That is, there must be at least one point on the red disk that is in the exact same position as it was when the red disk was originally on top of the blue one. Okay? And the fun proof is in the textbook. I won't go through it here, but it involves circles and compasses, and it's really an interesting read. What this leads to an application of weather. We now illustrate the power of this circle idea, and that comes from the proof that you'll read in the textbook, with an application to the weather. The North and South poles are always cold, however, they are not equally cold. Air pressure varies from time to time and place to place. These sentences just about exhaust our personal knowledge of meteorology. But we do know something about weather that practicing meteorologists do not. We have what's called the meteorology theorem. At every instant, there are two diametrically opposite places on Earth with identical temperatures and identical barometric pressures. Okay, so let's clarify that statement. Okay, at any instant in time, every location on Earth has both a temperature and a pressure. Every point on Earth has exactly one point that is diametrically opposite right here. Doot, doot. You can see doot, doot. Okay. The meteorology theorem says that if we have a globe before us with the temperatures and pressures written at each point, we can always find a pair of antipodal points on the globe where the temperature and pressure at one point are identical to the temperature and pressure at the other point. And that's kind of what we lead to, which is I think very quite interesting. All right, class. I know this was a quick introduction to this section. As always, you're going to have to read the whole chapter, a whole section to get a full, better understanding. But these are the video of the main topics. As always, if you need anything, I'm here to help.